Hey there, welcome back. This is part two of our section on refraction today. So this particular video in here is going to not necessarily talk about the math side so much, although we will get into that towards the end. But this talks about phenomena that have to do with refraction. In other words, some things that you see that are directly related to refraction. So we'll talk about some kind of optical illusions, and then we'll talk about some more realistic stuff that's kind of based upon the concept of refraction. And that'll lead us into next week's stuff as well. So for this particular section on here, like I said, I'm going to kind of talk sort of generically about some of the different things that we see, but every one of these phenomena that we see, one of these little, like I said, optical events, is based somehow, or at least partially, on the phenomenon of refraction. So again, refraction is the bending of light rays as they pass from one medium into a different medium. And I know I talked about a couple of these in the first video of this particular unit. But in terms of being able to see transparent materials, the only reason that we can perceive them at all is typically because they're transparent, yes, but the materials are actually different, that there is different densities of these materials. And so the light takes sort of a wiggle as it passes through these. So for example, I know it sounds funny to say it, but the glass of water should be invisible, right? You've got air, which is transparent. You've got glass, which is transparent. You've got water, which is transparent. So how the hell can we see it? Well, it turns out because all three of those things, glass, the water, and the air, have very different optical densities or very different indices of refraction, that every time a light ray passes through those materials, it takes this sort of a wiggle to it, and we can see these edges. And then as you add to that curvature, so like it's not a flat glass, it's a rounded glass, that causes even more distortion. So we're going to talk more about curvature later on. But just in this case, even if that was a nice, like an aquarium or something along those lines, beautiful flat pieces of glass, you would still see that change in light. And that creates something in your brain that goes, wait, something's in there. I can see that. There's a couple other things I put up on the screen real quick here. Moon bows or moon rings, you can see those. Sometimes it's more of a winter thing than a summer thing. Same thing with sundogs. These are definitely more of a winter thing. But these are other little optical phenomena that we can see. And I'll talk about some other ones as we go through this particular unit. So first thing, you can maybe kind of figure out that I'm going this direction when we're talking about density. One of the things about light traveling through air is that we forget that air itself doesn't necessarily have one index of refraction. You've seen this before, but you maybe didn't realize that it was refraction. So I want you to think about if you've ever seen a really hot surface and you've seen the little wiggles of whatever, the wiggles of the air, the wiggles of the light that's coming off of there. Because hot air rises and cold air sinks, right? So this is because the two different types of air, hot and cold, have different densities. One rises and one sinks. And so air is going to travel through those materials differently. They're slightly different media. And that hot air, cold air thing actually causes that phenomenon known as mirages. Now, mirages in the cartoons, I used to crack up when I'd see that because, you'd see, Bugs Bunny's walking across the desert or whatever. And then all of a sudden he sees that water off in the distance. And then he comes up and then there's like palm trees and camels and all that stuff. And that's not really what a mirage looks like. A true desert mirage is kind of like the picture that's on the bottom right here, where you don't really actually see palm trees and all that kind of good stuff unless they're originally there. But they don't magically have, all of a sudden an entire, castle or whatever out of the middle of nowhere. But what you did see was it looked like there was water on the horizon. And what this is due to is, again, due to the difference in density of hot air versus cold air and that hot air rising, what it's actually creating is a reflection of the sun. And so what you're seeing on the ground is a fake sky. And because that fake sky and water are similar colors, and it's actually because water is reflecting the sky also. But it looked like if you were walking across a desert and you're starving or you're thirsty, whatever, dehydrated to death, you would look in this particular picture over on the right and say, oh my God, it looks like water over there. And so you'd head over towards it and it would just be sand dunes forever. Same thing with this one up on the road. You may have seen this if you've been out driving someplace really hot. You see that in the summertime where it almost looks like the road is disappearing. And again, it's because you've got light rays coming down from the sky, but they're being reflected back up in a sense. They're bending, and instead of bouncing off and hitting the ground, they're reflecting or refracting is actually the correct word, back up to you. And so these light rays from the sky are actually reaching your eyes, even though they should be hitting the ground. So definitely a weird experience to see mirages when you see that. But again, a little short version of it is when you see those little heat waves. I can see a little mini version of that density change that's happening in there. Along with this, sometimes you can see this. This is related to, again, hot air, cold air tends to happen only in marine environments where, again, mirages tend to happen on hot sand, hot land surfaces. Well, looming is a kind of a cool thing. It's sort of the opposite, where you've got humidity is now thrown in there as well. We've got this cool layer down at the bottom and a hotter, layer up above it. And so you end up seeing this kind of the anti-mirage, as opposed to seeing the sunlight reflected up. You're seeing with an object that's on the horizon actually up above where it should be. So again, you see the sort of the floating boat sort of phenomenon, and that's sort of a weird version. It's sort of like an anti-mirage, if you want to think of it that way. But it's still the same idea. It's still that hot air, cold air density difference. One of my favorite mirages, so to speak, is rainbows. And rainbows is actually related to two different processes. It's related to refraction, and it's got a sub-process in there, which is called dispersion. So refraction is when light is bending through a prism, like this one at the top right. That's simple refraction. When you've got light that's bending through an optically dense material like a crystal that a prism would be made from, especially when the crystal is at some angles, so you can get some kind of fun plays of light as it's coming through there. You can get the spreading of white light out into its component colors. And again, this is because not only does light bend, but different wavelengths of light bend differently. And so as a result of this, you can get this spread of color, which is, again, a relation of refraction, but based on wavelengths. Now, if you take, instead of having one big crystal, but you have, trillions of tiny little crystals, you can have the phenomenon known as dispersion. Each tiny microscopic droplet of water acts like its own tiny prism. And so as the light hits that and bends through it, you'll get some different bending that occurs with this. Now, if you take a look really closely at this diagram up here, you can see kind of like a close-in focus of what's happening in a single droplet of water. That regular, kind of multi-light sunlight, basically white light, is hitting the droplet of water, and you're getting these bigger bends that are happening. So violet light bends one direction, red light does not bend as much. It tends to go a little bit straighter. And you kind of see this sort of bending, this fanning out of the different colors that's on there. And then when you have a whole bunch of these droplets, you can imagine millions of them, you end up with this really weird effect where the red light tends to appear on one side of the rainbow, and the blue light tends to appear on the other side of the rainbow. And this is an emergent phenomenon that happens, yes, within a single light droplet, but this is a combined effect of all of these different water droplets. So in order to have this happen, by the way, you need to have some moisture in the air of some sort. Like I said, you can do it with a little, like a hose, something like that, a mist of air. It can happen with rain and clouds, but it needs to happen generally when the sun is relatively low in the sky. Furthermore, the sun has to be behind you. So if you're looking at the sun, you're looking the wrong direction. So you need to have kind of an interesting combination of environmental effects in order to be able to see where the rainbow is. So again, it's usually earlier or later in the day when the sun's at a relatively low angle in terms of those being able to hit and then bounce back and get to you. But then again, you have to have kind of everything. You have to be facing the right way. You never face towards the sun to see the rainbow. You got to face away from the sun to see the rainbow. It's exactly the opposite direction from you, or pretty much the opposite direction from when you see it. And everyone says, well, how do you get double rainbows? Well, you can either have two different layers of water. You can have, like a cloud and water, something along those lines. They're actually circles, by the way. They're not truly arcs. If you ever get a chance to see a rainbow in an airplane, it's actually pretty incredible. It's a full 360. So it's kind of a neat experience. And again, this is just a combined effect called dispersion that allows you to see something based on refraction, the bending of light through water droplets. So this last one here is a little bit of our math today. This is a really kind of a weird little phenomenon that actually has some really important implications for us. We've actually learned to use this one. So here you have on the left a laser beam that's shining upwards into through glass into water. And then rather than shining straight out, which is what most people would say would predict it's doing, it's actually bouncing back inwards. So you can kind of see that it's hitting the surface and then bouncing back down. Now this only happens under certain interesting conditions, and this is part of our math lesson for today. So this particular thing is something called total internal reflection. And there's a phenomenon that goes along with this called critical angle that we need to talk about. So here's how this part works. This is our math part for this particular lesson. This is something I'm going to ask you to be able to calculate. So the way that this works is it has to be a situation, I'm going to go back to where you've got light that's coming from a higher index of refraction like water, and then trying to go to a lower index of refraction like the air that's above it. It only works that direction. It never works the other way. And this has to do with the fact of whether or not light bends towards or away from the normal. This is kind of what it comes down to. So you can imagine that down here in this particular zone, we have an incident ray coming from water, and it's going into air. Air is less optically dense. It has a lower index of refraction. So the light is bending away from the normal line. You can imagine a sequence of rays that not just this angle, but then I pull this angle. Let's see if I can get a pen going here. But I pull my angle a little bit further out. I go this way. This ray up here is going to bend even further from the normal. And if I go further yet, it's going to bend so far to the normal that at some point in time, it'll actually not be able to escape. It'll be right directly on top here. In other words, the index of refraction is 90 degrees. And it's literally kind of right on the surface. This here is called the critical angle. And you can use Snell's law to figure this out. We'll talk about this in our Zoom class or our Google Meets class to figure out how to calculate this. But again, our index of refraction, our index of, my goodness, my angle of incidence gets bigger and bigger and bigger. And so my refracted angle gets wider and wider and wider. And eventually my refracted angle is right along the surface. As soon as my incident angle gets any bigger than this, and you can kind of see it in this last one here, now this will no longer be able to escape. It is totally internally reflected and it bounces down inside. And now because this is reflection, the angle of incidence equals the angle of reflection. Once you get beyond the critical angle, you no longer have refraction, you only have reflection. And again, this only occurs when you're going from a more optically dense medium to a less optically dense medium, where that refracted ray is getting further and further and further away from the normal and eventually is right on that 90 degree. And again, if you take a look with Snell's law, you might be able to figure out kind of how that particular part works. But it's an interesting part. So this is actually really useful for us. There's two different phenomena that you're really familiar with maybe that you may have seen. Number one, total internal reflection is what makes diamonds sparkly. I don't know if you remember from yesterday's video, but the index of refraction for diamonds is like 2.42. It's one of the highest naturally occurring indices of refraction. Really, really high, which means you don't need to have much of an angle in order to have a lot of internal reflection. And this internal reflection allows diamonds to sort of collect that light and then sparkle it back at you. And when you combine this dispersion as it goes out, you can actually see the fire or whatever they call it that pops out of diamonds. But again, it's because of the fact that it's got a really high index of refraction that you can see it. And then they combine that with these different facets to give it a real shallow kind of angle to it, to keep that light bouncing around on the inside. It's one of the cool things about it. Second thing you may have seen is these fun little fiber optic lights. We'll talk about fiber optics more in a second. But if you have any of these little fan lights, they're real fun. You combine them with LEDs and they change color and they look really cool. But again, these little fiber optic lights, which is a real simple thing, but it's actually, this is the way more important example of what happens with total internal reflection. Because total internal reflection is what makes fiber optic cables possible. And if you've got high-speed internet at your house, you need to say thank you to fiber optics. Because what fiber optics allows us to do is you take a real high index material, something like a type of glass or certain types of plastic, oftentimes it is actually glass, and you can have light rays that bounce around inside this material. And this is an over-exaggeration. It's a piece of plastic as opposed to an actual piece of glass. But what this means now is that we can use fiber optics in combination with light to actually transfer energy. So in the olden days, and I'm talking about information energy, in the olden days of digital information, to get digital information down copper wires, you would have to literally turn an electrical current on and off. And that's what digital means. The ones and zeros of digital information is, one means that the electricity is flowing and zero means it's off, and it just flickers super fast. This 1010, and a receiver can then read that rate. It's almost like a type of Morse code, basically. But with electrical pulses, it doesn't travel super fast, and you have a variety of issues like heat. You get resistance from the copper itself, so the electricity doesn't travel that great through copper. I mean, well, but not like perfectly. And it's a relatively short distance that it can travel through there without overheating or losing some of that information. And then you get other things like other types of interference can affect it. As opposed to optical fibers, if you're literally just flashing a light from one end of the cable to the other end of the cable, these things can be incredibly long cables with basically zero loss in that on off, on off, on off. This allows digital pulses to travel very, very quickly, literally only about 30% slower than the speed of light, which is incredibly fast. So you don't have much latency is the term that they use with data transfer. Downsides to it, fiber optic cables are a little bit brittle because it is glass fibers that's in there. So they're a little bit finicky to hook up, but once they're in place, those cables can be much longer with very little data loss. And so you can actually have much more data in a much smaller tube, so to speak. And you can have these bundles of cables that actually contain multiple factors more information than old copper wires could. So there you go. Fiber optics is actually one of the key parts of a really important use of refraction in your everyday lives. So I hope that you've enjoyed that particular part. And then the last thing is what we're going to do next week. And I just want to mention this as well. Lenses are something else that we use where we actually take little pieces of plastic and we curve them and then let the light pass through them in different ways. And lenses are something that are a way that we're going to harness that power of refraction and use it to focus images in different ways. And that's the part of our next week's unit. But I wanted to kind of put this in here to kind of note that this is probably one of the, in human history, one of the most important types of refraction that we've used. It's allowed us to see into the smallest objects. It's allowed us to, not die from accidental things and be able to find food, thanks. And then it's allowed us to actually see out into space. So harnessing the power of refraction is actually one of the most incredible, cool things that we've learned how to manipulate a bit when it comes to light. So there you have it, refraction today, and some different optical phenomena that go along with refraction. I hope you enjoyed it, and I will be seeing you next time. Enjoy.